will be on November 10th. December 8th, we will have COVID and Kids. Dr. Dan Cooper, Professor of Pediatrics at UCI's Institution of Immunology.
Maybe.
And January 12th, Perseverance rover mission to Mars. Megan Cox, engineer at NASA JPL. So tonight, we're going to do something a little bit different. The housekeeping rules, though, are still very simple. We're asking for us, in order to not distract from the presentation, I'm going to ask everyone to mute themselves until we have our Q&A session. If you have a question, please save them for the Q&A and raise your hand to be called on. The moderator will give a limited amount of time for each person to ask and answer the question, just so we can get as much time with Dr. Fenty as possible, because I think there will be a lot of great questions. I already got some in advance. Please be kind and respectful. Not that I need to tell any of you this, because you always are, but during all communications, you know, it's kind of crazy, but we can mute you or eject you if necessary, but we know we have amazing people on the line. Any additional technical questions or questions not related to the presentation, please directly message to me or Elizabeth. And then, of course, last but not least, have fun, be curious, and make friends. For those who are unable to join us or would like to view this broadcast at a later date, we will be recording it and making it available on YouTube. Now, with no further ado, please welcome Jay Whistling, an incredible friend to Discovery Cube and Innovator's Vice Chair. Welcome, Jay.
Well, thank you, Bree, and thanks to everybody that's joining us this evening. And it is really a pleasure to have Dr. Fenty back with us. He spoke to us a couple times, and we're anxious to learn more about his research. Dr. Fenty is an MIT grad. He has worked as a climate scientist at NASA's Jet Propulsion Laboratory in Pasadena since 2010, I believe. Dr. Fenty's research involves close collaboration with JPL, oceanographers, glaciologists, and other scientists to reconstruct the climate variability of Earth's oceans and sea level rise. He is currently researching the connection between ocean warming and the melting of the Greenland and Antarctica ice sheets. And without further ado, Dr. Fenty, the talk is all yours.
Okay. Well, thank you very much, Jay, and all of the organizers of the Discovery Cube. Welcome, everybody. I'm very happy to be back at Discovery Cube virtually. I can't wait to go back to all of the different Discovery Cubes. I really enjoy it, and I strongly believe in the mission of Discovery Cube. I've had great talks before, and with great interaction with you all, Discovery Cube supporters. And I'm going to share my screen right now. Jay is going to tell me whether it works. How does it look?
Looks good, Ian.
Okay, good. And I'll just go right into my my science talk, which is a kind of a high-level overview of sea level rise, the science of sea level rise, which I like to think of as a smoking gun of climate change. Before we go into the science of climate change, just wanted to give a little bit more back about me. Jay gave a great overview, but just some other, humanizing context. I grew up in Southeast Pennsylvania. I'm the oldest of 6 children. I went to public school. In Philadelphia, we had a Ben Franklin Science Institute that we would visit on school field trips, which kind of reminds me of the Discovery Cube. I did my undergraduate degree in central Massachusetts at Worcester Polytech. I worked for a few years as a business consultant. Went back to school for a PhD in climate physics and chemistry. And then I spent a few years in training as a postdoc at JPL and Caltech. And since 2010, I've been since 2013, I've been a scientist at JPL. In 2020, of all of the crazy things about 2020, they have 2 special things for me. It's a 20-year anniversary with my wife and a 10-year anniversary being in Southern California. In fact, 2 days ago was the official 10-year anniversary of being in Los Angeles, which was really great for us to celebrate that. I really enjoy living here and being here. This is a photo that we took a few weeks ago in Greenland as part of our survey mission of how the oceans are melting Greenland. And we were one of the few missions that NASA allowed to go in the field this year because of COVID. It was just a wonderful experience. So this is the outline of the talk. I'm going to cover how fast sea levels are rising, why should we care, how NASA measures sea level from space, the connection between global warming and sea level rise, projections of future global warming and sea level rise, and some things that all of us can do in our own lives to try to mitigate, reduce, maybe even cancel global warming and sea level rise. So just right from the beginning, I have this very simple, but I think very impactful plot that shows global sea levels elevation over the last 140 years. What we see over this time period is sea levels rising about 9 inches. Some of the data that we have is based on reconstructions from a network of global tide gauges. Many ports around the world have continuous tide gauges, and through being very careful reconstruction of those old logs, scientists have been able to make pretty credible reconstructions of sea levels dating back since 1880. We can go further back, but then we need to use much less direct methods. In the last, or rather since 1992, so almost 30 years, NASA has had a special kind of satellite that measures sea level from space, which I'll talk about in a little bit. And the tide gauge measurements and the satellite measurements agree pretty well with each other. The satellites we trust a lot more than the tide gauges, and so I plot them both on the same curve here so you guys can see that they don't exactly agree with each other, but they agree pretty well. Now, sea levels are not just rising, but they're also accelerating. In the first 40, 50 years of this period, sea levels were rising very slowly. But now in this later period, in the last few decades, sea levels are rising now 6 times faster than they were at the turn of the 20th century. So it's a major question for scientists why sea levels are rising as fast as they are. We know why they were rising in the early period. The Earth has been coming out of an ice age for thousands of years. Greenland and Antarctica and glaciers around the world were much, much bigger in the last ice age. And it's been about 10,000 years. They have been slowly melting ever since. So sea levels were rising slowly in this earlier period. And then, corresponding with the rise of the Industrial Revolution, and sea levels began to rise faster and faster. So why should we care about sea level rise? Well, simply, I come up with a couple reasons which I think are of interest to all of us here on this talk. Sea level rise will obviously cause permanent flooding of low-level areas, some of which are very valuable natural places like wetlands, and other places like here the El Segundo power plant and the Balboa Saloon in Newport. According to a recent report, $100 billion of California property is threatened with 3 feet of sea level rise, which is kind of what we expect to happen in the next 100 years or so. And an important point, which it didn't really hit me until recently, after some of the flooding from some major hurricanes. It became kind of more clear to me and more of a topic in our community that well before many areas are permanently flooded, they will just be uninhabitable. Because how many days of the year do you want to deal with ankle deep water in your driveway? Like I'll deal with about 10, but if I'm doing months at a time of not knowing whether I have to wear galoshes, having my lawn be flooded, having my property be flooded, having to continually pump out my basement or, clean out my crawl space, I'm going to move. And so that's an important point. Lots of infrastructure and property will be lost well before sea levels cause them to be permanently flooded. Another point is in California, we have 800 miles of iconic shoreline of sea cliffs. Sea level rise will cause ocean waves to break more frequently at the base of the sea cliffs and cause them to erode. Of course, that threatens property, but also, destroys this iconic feature of our state that draws, untold millions of dollars worth of tourism money, and also is a central part of many communities. And not less than that, California, we have magnificent beaches. As sea levels rise faster and faster, the beaches will not be able to expand up inshore fast enough, and that will cause our beaches to retreat and shrink. Can you imagine the loss of our California beaches? Well, that's very certainly a possible outcome of sea level rise in our state. This is a plot recently made that shows the vulnerable areas in Orange County, areas that are vulnerable to sea level rise even today, and at risk, here it says, of a 100-year coastal flood. Well, a 100-year coastal flood today is a 50-year coastal flood in 2040, is a 10-year coastal flood in 2060, is an annual coastal flood in 2080. These are areas that will most likely be abandoned before the century is out because of the inconvenience of having to deal with seawater at your door for months at a time every year. So so all that aside, because I've told you how sea levels are rising and why we should care. Now, I work at a NASA laboratory. This is our bread and butter. I want to tell you about how we know sea levels are rising. These days, like I said, we don't rely on tide gauges anymore. We use satellites. Since 1992, we've been making continual measurements of global sea levels from space. And the principle of the measurement is quite simple. The satellites, they fly in an orbit around the planet, and they are continually sending down electromagnetic waves, radar. The radar waves travel from the satellite, which is labeled 1, down to the sea surface, which is a little cone, and there's a number 3. And then the radar waves bounce back to the satellite. So we know how fast the radar waves travel. They travel at the speed of light. We can measure very carefully the amount of time it takes for that radar wave to travel. And through a simple equation, we can calculate the distance between the satellite and the sea surface. We know where the satellite is because of GPS, which is labeled 2, and ground-based ranging stations, which are labeled 5. These measurements are made continually around almost the entire planet. There have been 4 satellites in this series: Topex Poseidon, Jason 1, Jason 2, and Jason 3. And in less than 1 month, we'll be launching the next member of the family, the Jason CS mission, which I'll talk about at the very end. But the point is that we've been making these measurements from space for decades, and we know very precisely that sea levels are rising, and we even know where they're rising and how fast they're rising, just as a function of space. And that's the result of it. The result of those measurements are shown in this map here. Red, orange, yellow, and those are all places where sea levels are rising. Green, blue, and dark blue, purple, those are places where sea levels are falling. So in almost all places, sea levels are either stable or rising, with an average of a little bit more than 3 millimeters per year. This is something which comes as a big surprise to most people, and even to myself. At first, you would think that if you add water to the ocean, the sea levels like your bathtub would go up everywhere. But in fact, as the climate changes, heat is absorbed in the ocean in different places. The winds of the ocean change, and that pushes seawater around in different ways, causing it to pile up in some areas and depress in others. So although we know that global oceans are warming and water is pouring into the oceans from melting glaciers, the actual pattern of sea level rise is not uniform. And now this is a pretty long-term trend, but it's not to say that these trends will continue. If you look, I put an arrow here at around the little bit more than 3 millimeter per year mark, which is the global average of all of these colors. But you'll notice that California's average is a lot lower. In fact, it's almost 0. And the reason for that is because, and as the climate has changed, wind patterns around California have pushed water away from the coast. And that pushing of the water away from the coast has kind of given us an artificial sense that sea levels aren't really rising very fast. But that change in winds is not expected to continue forever. And when that wind pattern does change, California sea level rise, California will likely experience a few decades of very rapid sea level rise. So far, we've kind of been in a bubble, not really experiencing the worst of what is likely to happen, but in the coming decades, California is likely to get the chickens will come home to roost, which is unfortunate, and I'm sorry to report that, but that is the conclusion of oceanographers. So why do we think global warming is related or responsible for sea level rise? As I mentioned early on, sea levels have been rising for more than 10,000 years as the climate has warmed. Well, of course that's true. The increase of sea level rise over the industrial period, though, we think is very likely closely linked to the increase of greenhouse gases in the atmosphere. A canonical plot showing that, updated just today, October 2020, is the plot on the top left of your screen, which shows atmospheric CO2. CO2, of course, being a major greenhouse gas. Since the beginning of an extremely valuable and precious record set up in Hawaii. You can see that since the late 1950s, atmospheric CO2 on Earth has slowly increased. In fact, in the earlier period, it was increasing at about 1 part per million per year. In the later period, it's now increasing at about 3 parts per million per year. So even though we have known for much longer than the 1950s that CO2 is a greenhouse gas, and we've known easily over my lifetime that CO2 is a dangerous greenhouse gas that can cause global warming, humanity as a whole has done very little to stem the increase of CO2 in the atmosphere. In fact, the situation is getting worse every year. Alongside this increase of the CO2 greenhouse gas and other greenhouse gases, the global mean temperature on the planet has increased by several degrees. We can say by 2.5 degrees or so. I think, I'm sorry, the label here should be Fahrenheit on the top right panel. Almost over the entire planet. This map here on the top right doesn't show the increase of temperatures at the high latitudes, like in the Arctic and around Antarctica, where the global mean temperatures have increased even faster than that. So we know the greenhouse gases are going up, and we know the global mean temperature has increased, but we live on land. We live on land and we breathe the lower atmosphere, and what we generally don't think about is how much of global warming is happening in the ocean. In fact, the ocean absorbs about 90% of the excess heat from global warming. In other words, the ocean is really absorbing almost all global warming. An elementary exercise I give to students is I ask them to figure out what the temperature of the Earth would be if the ocean weren't there to absorb all of this extra heat. And the answer they quickly realize is that Earth would have already become uninhabitable to humans if the oceans weren't absorbing 90% of the extra heat from global warming. Well, as the ocean absorbs all this heat, the seawater warms up and the seawater expands. Just like many materials that you're familiar with, as they heat up, they expand. Seawater does the same thing. But because the oceans are bounded on the side by the continents, when the seawater expands, it only has one way to go, and that's up. And the warming of the seawater and the rising of the sea because of the warming, we know is now causing about 40% of global sea level rise. So where is the other 60% of sea level rise coming from? Another set of satellites that we use, called the NASA GRACE satellite, whose mission recently ended, but has now been continued with a new set of satellites called the GRACE follow-on satellites. They measure the change in mass of the planet. And over most places, say over Newport or over Discovery Cube, the mass of the planet doesn't change very much. You know, maybe some people will move in, some people will move out, some people will build a new house, but overall, the mass doesn't change. Where mass does change are places where ice is melting rapidly. If you have a mountain that was covered in a mile-thick glacier, and now that glacier is gone, the GRACE satellite will measure that as a huge decrease in the amount of mass in that location. These GRACE satellites fly around the whole planet and give us measurements of mass change, and where some of the biggest signals that we see are in the Antarctic ice sheet and Greenland ice sheet. And that's what I try to plot, that's what I'm plotting here. You can see from 2002 to 2016, which was the nominal end of the primary GRACE satellite, mass loss in Greenland and Antarctica was steady, and some argue increasing over this time period. Where the ice is melting in Greenland and Antarctica is indicated by the red. Where the mass is increasing is indicated by the blue. Many people see the blue in East Antarctica and they wonder how that could be. Well, the answer is that as the climate warms, there is more snowfall in some regions of the planet. There's also more precipitation in some regions of the planet. But for Antarctica, in this sector, there's slightly more snowfall. That increase of snowfall, however, does not offset the loss of ice due to melting in other sectors. That's why you see the Antarctica curve. It may not be as great as the Greenland curve, but it is trending steadily downward over this entire period. I can tell you I have many colleagues who work on the Antarctic and Greenland ice mass problem like full time. And as I showed you in that earlier picture of me in Greenland just a few weeks ago, part of my work involves trying to understand what the ocean warming role is in the loss of ice sheet mass on that island. Suffice it to say, the Greenland and Antarctic ice sheets have been shrinking. We know that the atmosphere has been warming, and we know the oceans that are in direct contact with many sectors of the ice sheet have also been warming. Together, these facts lead us to the conclusion that it's a warming planet that's driving this acceleration of melting of those huge reservoirs of fresh water on land. So what are some of the projections that we expect about sea level rise in the coming decades? For reasons which are mainly historic, many scientists make projections or focus on a time period from present day to the end of the 21st century. And maybe that's because they think, well, you know, they'll live in the 2010s, 2020s, you know, up to the 2050s, and their children will live from today until 2080, and their grandkids will live from, you know, 2060 until 2100. So this is kind of the time period of their lives and their children's lives and their grandchildren's lives. They don't generally think beyond that. Maybe it's human nature to just think to your grandchildren and not 7 generations. But you know, this is what we generally do. And when we think about the future, it all kind of comes down to how much greenhouse gas there will be in the atmosphere. And of course, that is directly related to how fast we will be pumping greenhouse gases into the atmosphere. So the scientists use this term representative concentration pathways, or RCP, as kind of a shorthand to describe different ways that humanity might respond to the threat of global warming. And you see here on this plot, the y-axis is the amount of CO2 in the atmosphere. And as I mentioned today, we're at about 414 parts per million in late 2020. And so we've come up with these different curves, RCP 2.6 being a curve in which very, very quickly, soon from now, humanity makes dramatic changes in how we acquire energy and fuel, transportation, etc. And greenhouse gases rise only a little bit, but then slowly fall throughout the rest of the century. If humanity followed this RCP 2.6 trajectory, which is extremely unlikely, global warming will be kept below 2 degrees Celsius. The worst case scenario in red is what we call RCP 8.5. And this is kind of a scenario that's meant to scare everybody. It's the one in which China builds a new coal power plant every week, and the US decides not to engage, and the entire Western world decides not to engage in any renewable energy policies. And the size of everyone's SUV grows by a couple % a year, and our air conditioning, we provide all of our energy by burning natural gas, and it's the worst case scenario. It's the complete head in the sand scenario, a total disaster. Most policymakers think that we will be somewhere between 8.5 and 6.0, or that the scenario, because for example, coal is less attractive these days. There is less coal being built, and some people are driving electric cars. Maybe that'll become that trend will become more popular as time goes on, and different states have enacted different building standards, and states like California and Massachusetts have laws that require that a certain fraction of their energy is produced by renewable sources. So currently, some people think that we're more on an RCP 6.0 than an 8.5. But the point is that this is kind of how we think about it, and we don't know which trajectory we're going to end up being on, because of course we make our own future. But just mentioning that as context, I will give you some projections for the different scenarios going forward. I'll give you the best case and the worst case, and we can make reasonable expectations that unless we are just completely stupid about this, we will probably end up somewhere in the middle. As I mentioned, the RCP 2.6 scenario assumes that we make a serious effort to constrain emissions, and you see that the global mean temperatures rise by only about 2 degrees relative to pre-industrial temperatures. Of course, the Arctic Ocean, you can see it gets much warmer, and I believe even in RCP 2.6 there is essentially the loss of essentially the entire Arctic sea ice. In the complete doomsday scenario 8.5, global mean surface temperatures are higher by an average of 6 degrees a year. 6 degrees a year in Southern California may not seem like a lot, but of course this doesn't convey that in many places the 6 degrees will be loaded in a number of days of extreme heat. And where I live in Pasadena, there were a few terrible days this year that I experienced, and the idea of having a few weeks of more than 110 degrees Fahrenheit might drive me out of this beautiful part of the world. With respect to sea level rise, in all scenarios, sea levels are expected to rise. And why is that? Because even at 2 degrees Celsius warming, the Greenland and Antarctic and mountain glaciers will continue to melt to contribute to sea level rise. The oceans will continue to warm and expand and contribute to sea level rise. And those processes will continue for thousands of years. In the worst case scenario, 8.5, we actually don't have a very good idea about how bad sea level rise will be. And that's because we don't know how the Greenland and Antarctic ice sheets will respond as the climate continues to warm. Assuming that they respond very conservatively, scientists have come up with about 1 meter of sea level rise as the expected at the end of the century globally. But that's the consensus. Many other scientists, though, think that the worst case scenario is far higher than that. Okay, so enough doom and gloom. Let's talk about the last couple of slides, what it is that we can do about this. I am not a policymaker, but I can report to you the statement from the recent IPCC report, which says very plainly that limiting climate change requires substantial and sustained reductions of greenhouse gas emissions. That should be pretty obvious to anyone who pays any attention to global warming. If greenhouse gas emissions and carbon dioxide levels in the atmosphere are driving global warming, then we need to reduce the amount of greenhouse gases that go into the atmosphere, plain and simple. And finally, people ask all the time, what can they do? What can I do? What can they do? What can you do to help get us on one of those more efficacious RCP trajectories? And there are a couple good recommendations out there. For example, you can promote climate literacy in your home and community. Everyone who's on this talk today is doing that, but continue to support climate education. Discovery Cube and other organizations have, as part of their mission, to increase climate literacy in our communities, and I strongly encourage that those organizations are supported. A lot of people also, they don't realize exactly, and of course, why would they? We didn't grow up learning this, just what our carbon footprint is. Carbon footprint is just a fancy name to say how much greenhouse gases we are putting in the atmosphere. Like, I find it to be extremely informative to learn about my own carbon footprints and the carbon footprints of typical people who live typical lives like all of us here. There are many places where we can make relatively small changes and really decrease our carbon footprints. And the one that really stood out to me was a study that I saw recently that said that if eating a more plant-based diet actually has a huge impact, like an outsized impact on carbon footprint, a much bigger impact on carbon footprint than I really thought was possible. So even just eating less meat, having a couple days a week be vegetarian days or vegan days, can have a huge positive impact on our carbon footprint. And I encourage people to learn about that. It's not that you'll get skinny. It's not that your blood pressure will go down, because I'm not that kind of doctor. I have no idea whether that's true. But as far as your carbon footprint goes, it's like a no-brainer way of doing it. Okay, another one is replacing your fossil fuel consumption with renewable energy sources. Putting solar panels on your roof means that the big energy producing facilities don't need to burn fossil fuels. If you drive an electric car and you power your car with the solar panels, well, you've just stopped directly burning fossil fuels to get around the neighborhood. These are things that are not within the reach of everyone in our communities, but they're certainly within the reach of many of us. And it's something that we should do if we can, to set a good example for our neighbors and to make it make it more commonplace. Make it seem more normal. About half the new cars sold in Norway these days are electric, which is amazing. You go to Norway and every car is just silently zipping around. It's become the normal thing to do. And we've made a lot of strides on that, but we can do a lot more to replace our combustion engines with electric cars or hybrid cars. And of course, in these times, which are a struggle for many of us, given COVID and given all the nonstop barrage of news and what seems to be a downward spiral of some things, including the environment, it's important to maintain a positive attitude, because That's the only way that we can, get up and do something, even if it's not for ourselves. This picture was from a science march, which I really liked. See this young person holding up a sign, "There's no planet B." I think that was just really clever, and to see all those young people and parents, because of course we leave the planet for them, and the more we can do now, the easier it'll be for them in the future. And the last thing I wanted to mention to you, that everyone, well, there's a very exciting opportunity coming up, that the next satellite altimeter, as part of that family of satellite altimeters that I mentioned earlier, is going to be launched in November at the Vandenberg Air Force Base, on a SpaceX rocket, which is so exciting. Now, you can't get onto the Vandenberg Air Force Base unless you are in the Air Force or working directly on the mission. And in fact, because of COVID, even most scientists and engineers are not allowed onto the base. However, there are many places that you can see the launch in the neighborhood around the Vandenberg Air Force Base. I went to see a launch of a recent mission to Mars a few years ago from one of the popular public viewing areas, and it was really amazing. So, if you can get yourself or your family and some neighbors and some friends up to Vandenberg Air Force Base on November 10th, just make a day of it. Get out there. I will happily send the information that I have about the best viewing spot to anyone who's interested. Bring your binoculars and your lawn chair, and it's amazing. We get pretty close, and I'm going to be there. I'm going to be there with my NASA hat and my NASA kazoo, and it's going to be a party. This is a really great mission, and just like I said, 27 days from now. So, okay, I've gone over my time. Thank you very much, and if anyone has interest in answering any questions, I'll take some now.
And Dr. Fenty, just first, thank you so much. It's such an inspiration. And obviously we love the last part, which is staying positive, because what you shared with us is pretty scary in many respects, but it still says that we can make a difference. There are a flood of questions, and I don't think we're going to be able to get to all of them, but we certainly can try. One of the key things that we're always talking about at Discovery Cube is creating a sense of STEM identity and wanting to be curious and connect in science. What got you interested in a career of climate science? What was it that really pushed you into this field of study?
Well, my first real experience with climate science, or environmental science, as it was called when I was a youth, was in the Boy Scouts. We had a good summer camp. We had a great summer camp program that involved, a whole host of environmental awareness merit badges. When I got towards the end of Boy Scouts, I got to be one of the people who taught those classes at camp, and I just had a blast doing it. When I enrolled for my undergraduate degree, there was no equivalent degree program offered at that particular school. So I took classes in environmental policy, but I didn't see that as a career. When I spent a couple of years working as a business consultant, I had these great experiences with the practical application of modeling, in the sense that we were, simulating businesses and business problems and supply chains. And I just thought, okay, this is I studied this in school, and it's really interesting to see how this can play out in the real world. At that time, there wasn't actually a lot of hard data. So we were using these models, but we weren't able to really compare the outputs with real observations. And I thought, oh, I would really love to find a way to merge data collection and simulation and prediction. And I'm still very interested in environmental ideas. So fortunately at the time I lived in Cambridge, and so I just went around and knocked on the doors of different professors at the universities and I told people what I wanted to do until I found someone who was willing to enroll me in a PhD program. And then, once you're kind of in that world and you see the thousands of ways you can, turn that into a career, because before you get into it, it's just, you don't know, it's a black box. Once I was there, I saw that there were a lot of opportunities. And if you can't think of ideas to do in climate science, you got big problems, because it's the sky's the limit. So that's kind of like, that was kind of my arc. And I've had a lot of great opportunities and support throughout the years, especially getting to JPL and staying at JPL.
That's great. When you think about Discovery Cube, and thank you so much for enjoying our centers, and we have to get you out to LA. I know you're closer to there. Are there any exhibits you'd recommend that could be incorporated into the Science Center to discuss sea level rise and global warming, or ways that maybe even AI can kind of play a role in that, so we can see kind of how it might progress differently?
Well, that's a good question. Today I was going for a hike in the morning with my wife, and we were tossing ideas around. She's a good sounding board. And the idea that I was struggling with was how to communicate the idea. I don't have an answer, but there's a topic which is really, I think most people they don't really appreciate it, and it's a little hard to communicate it, is how long is the memory of global warming in the climate system? I was thinking of these different metaphors, and I was thinking, okay, the half-life of a radioactive isotope, and my wife was like, no, definitely don't use that. And I said, and the one that she came up with was smoke after the forest fires. Mm-hmm. Even when the fires stop, right, the valleys are still smoky for some time, right? There's a lag. It takes a while for the system to return to its normal equilibrated state. For greenhouse gases, that time is not days, it's not weeks, it's not years. It's more like centuries to millennia. It takes an awfully long time for the Earth's natural systems to fully take up all of the extra carbon that we put into the atmosphere. I think this idea is very, very important, because some people, I believe, are under the impression that if only we stopped our greenhouse gases today, then the climate would return to normal. But it's not true. When you release greenhouse gases, it lasts for 1,000 years, right? Maybe not that one molecule, but that increased level of CO2 in the atmosphere will last for 1,000 years. And I think if people had a sense of just how long the consequences were, that it might shift their thinking about burning fossil fuels. Because it's easy to do it. You just don't think about how long the consequences are going to be.
Well, maybe a specific question that might be good as a secondary one to one you just answered is, there's some specific questions about hearing that the Earth temperature rise leads to the CO2 rise, or what is the main contributor to CO2? Can you share your thoughts on that? Because there's lots of ways, but anything specifically that...
Oh yeah, there are many ways in which Earth's temperature rise can lead CO2 increase. Just like a simple example, there's a lot of carbon. I live 1/4 of a mile from the mountains here at San Gabriel Mountains, and 3 miles from my house was the edge of the burn zone for the Bobcat fire. There is carbon stored in trees and in leaf litter and in bushes, all in that 100 square mile area that burned. As the climate warms up, those areas are more susceptible to burning. So a warming planet leads to more forest fires, and that then causes more CO2 released into the atmosphere. And there are many examples like that. But today, the primary source of carbon dioxide in the atmosphere, of the, let's say, extra carbon dioxide in the atmosphere, is burning of fossil fuels. So it's a kind of like a, maybe somewhat of, it's an argument that some people make against the reality of global warming. They say, well, there are all these things that cause CO2 to rise, and it's not just my Escalade, you know, it's also the CO2 or methane that's being emitted from a bog. It's true, but we can actually, carbon has isotopes. We can track the different isotopes of carbon in the atmosphere. We can identify their sources. And we know that the excess carbon dioxide in the atmosphere is from burning of fossil fuels, not primarily from, let's say, so-called natural sources.
So I think this kind of goes into that, another question, since all plant or animal human life on Earth is CO2 based, why is the percentage of CO2 so low? Also, plants and trees love CO2.
Why is it so low?
That was the thought.
Oh.
It's getting higher, but yeah. What are your thoughts on that?
What sets the equilibrium level of CO2 in the atmosphere? Well, there are a ton of, there's no easy answer for that. There are a lot of negative feedbacks in climate, right? So like you have sources and sinks of carbon dioxide, right? And like any system will reach an equilibrium when the sink is a function of the magnitude of the quantity. That's the first order response. So for example, what is like the natural long-term geological source of carbon dioxide? It's outgassing from volcanic activities, volcanoes. Volcanoes, like they don't care about humans. They have their own agenda and they are spitting out, gases from deep within the earth, and some of those gases are greenhouse gases. So that's just like a source which is independent of all humans. And then there are sinks. So one of the primary sink on geological timescales is carbon absorption in sedimentary rocks. The carbon is in the atmosphere, and it is absorbed by organisms in the ocean which die, settle to the bottom of the seafloor, and over millions of years, the seafloor is subducted and that carbon goes back into the ocean. Back into the crust. Unlike shorter time scales, you have plants and whatnot. When there's more carbon dioxide, they can absorb some of that into themselves. And the ocean is another case. There's an equilibrium amount of carbon dioxide absorbed in the seawater. When you increase CO2 in the atmosphere, some more of that is dissolved. So you have many feedbacks which draw CO2 down. And, it's a kind of a God question why some of those sinks have the strength that they do. But let's just say, ... it turns out that the planet in modern times, let's say modern pre-industrial Holocene, likes to have about 320 parts per million. If there was no life in the ocean, if there were no plants on land, then the equilibrium level would be higher. Okay.
That's
kind of like a long answer, but it's a
fascinating way that you answered it. No, I appreciate it because I think it's really important for us to hear from you. And just thank you so much again. This will not be the last time. We're going to keep asking you to come back as long as you'll say yes to us, Dr. Fenty. So you'd say yes, right?
Love it.
He's coming back. Okay. So we always try to end by 8. So I'm going to move on, but I just want to say thank you so much to Dr. Fenty. And I would love to welcome and introduce Janet Ray, Discovery Cube's Innovator Chair, to end the evening for us. Janet. And thanks again, Dr. Fenty.
Well, I also want to thank Dr. Fenty. Amazing. This whole evening has been fascinating because equilibrium it's so complex. I must tell you that when you showed that video, or not video, but the slide of the Balboa Saloon, which we don't really go to, I got out my scuba gear because well, here it is. It's actually pretty cool. Thinking that Waki and I, who live on Bay Island, may need to be using it sooner rather than later. But this evening has been much more than the rise of the water. The whole thing is fascinating, and if you don't come back, you're in trouble. We just think you've done a fabulous job, and thank you, thank you, thank you. And I also want to thank all of the rest of you and the innovators for joining us this evening. I know that this is probably not the first Zoom you've been on today, probably not the second Zoom, but it is so important. And Dr. Fenty, thank you so much. Really,
Happy
really
to come back anytime.
And we're thrilled at the Innovators to be able to have this virtual science speaker series where we're calling it Cube Talks, and similar to some other kind of talks, but it's an opportunity for all of us to nurture our experience while we're going through a tricky time. And please note, put on your calendar, second Tuesday for the next 12 months from 7 to 7:45 or 8 for the Cube Talks. And I also want to share with you that one thing that I've done for the last 10 years as being the chair of the Innovators is to be able to share what's coming up. And Dr. Amy Zimmer-Faust is coming on the November 10th at 7 o'clock. She will be discussing the local watershed, coastal and wastewater surveillance. And then in December, we're going to learn how our children are faring with COVID with Dr. Dan Cooper, who is from UCI. So these are very, very relevant. Then starting in 2021, believe it or not, where we're going to start out with the rover Perseverance on Mars and follow up with combating those nasty mosquitoes, ankle biters. Some of you have experienced it. I have, Waki hasn't. And then there's the talking monkey business at the San Diego Zoo. Delete Santa Ana Zoo, our local zoo where Janet Yamaguchi and her husband have been involved for years. So we've got a lot of things coming up, and all I say is be part of the new normal at the Cube, where we use innovative solutions to keep our Cube family informed. Let's hang together, be safe, and come out stronger through science at the Cube. Thank you, and good night.
Thank you.